Hey, we're back. All right, so any questions?
Did I miss the next homework assignment, or is it not?
It's posted.
Okay.
Yeah,
Oh, it is posted?
it should be.
I saw the programming assignment was up, but I didn't see the homework. I would be crazy there.
The programming assignment's up, the homework should be up. Has anybody seen the homework?
The homework
Check
due
it out.
a week from
Today?
this Wednesday.
You're gonna make me nervous that I didn't like hit the publish button or
Well,
something.
I might have just not
I
seen it.
mean, I might have not seen it either, because usually my first place to look is just the to-do
Sidebar,
list.
yeah.
Yeah, the sidebar to-do list.
All right, let me make sure I hit the publish button.
I think.
That
All
took a
is
second.
Understandable.
Yes.
I definitely had to do double take there. Sorry, man.
Yeah, hit that
I was
publish
like,
button.
who's that guy?
A little late quarter to join as a student.
It's cold up there.
Yeah.
Yeah, you definitely shaved at the wrong time. Dude.
It's trying to publish it.
When is it
Suffering
supposed-
swings and arrows.
When is it supposed to be due exactly?
Oh, it was due today, sorry.
No.
Well,
Well, it wasn't posted, so
Yeah.
I guess we're all out of that one.
Yep. Oh well. You can take the course again in winter.
I guess it's a class period to do it.
Yeah. All right.
only for
We can make it a
grants.
collaborative
There we go.
assignment.
Okay, so let's do on next
Let's
Monday.
do
a
the,
week
it's due on
from now, yeah.
Monday.
And the programming assignment is due on the 30th as well, right?
yes.
I believe so.
Okay.
Yeah.
Two pages, two documents.
I used a very fancy typesetting system to draw the graphs and stuff, so I hope you appreciate the effort that I put into it.
LaTeX.
Yeah.
You know what does not appreciate the effort though? It's apparently the internet connection because it's taking so long to download a single.
Just the
megabyte.
starting.
4 minutes left.
Six
of 1
minutes.
megabyte.
Whoa.
Oh, nope, it stops.
Dude, the speed, man.
There we go. 6 minutes.
It's like stereo
So you
commercial.
want to do the lecture first, and we'll get back to that at the end of
Maybe,
class?
maybe we'll do that.
Yeah, I got a better idea.
There we go. I seriously think
The
so.
local copy.
There we go.
Alright.
Oh, this is even better than LaTeX.
Yeah, it makes it look like it's hand-drawn. It's really fancy. So, question 1. So I want a precedence graph. We looked at this a little bit on Friday. So basically you can show which statements are dependent on other statements before it, and you can make a directed graph. So 6 nodes, S1 through 6, and just show me which statements depend on other statements before it, so we can decide how to parallelize it. 2, make an adjacency list, adjacency matrix, and incidence matrix for this graph. So 6 edges and 5 vertices. 3, there's an adjacency matrix. Show me the graph. Yes?
I remember what adjacency is, but what's incidence?
Incidence. So if you have,
All of this was on Friday too, right?
I think all of this was on, well, some of it might have been on Thursday.
Just the past week in general.
So here's a vertex, here's an edge. This edge is incident to
Okay.
this vertex. And V2 is adjacent to V1. So there's a adjacency graph for a directed, adjacency matrix for a directed graph, so draw the directed graph. So you can take from to be on your vertical and 2 on your horizontal. 5, there's 2 graphs given by adjacency matrices. Are they isomorphic? If they are, find me the bijection of the vertices. If they're not, convince me that they're not. 6, there's a wonky looking graph. For the following list of vertices, is it a path? What's its length? Is it simple? Is it a circuit? So there's some paths to consider and analyze them. 7 is another graph. Does it contain an Euler path? If yes, draw it. Does it contain an Euler circuit? If yes, draw it. And then question 8, same thing for Hamilton circuits. Does it have a Hamilton circuit? If not, convince me that it doesn't. And 9 is Dijkstra's algorithm, which we're going to talk about today. So use Dijkstra's algorithm to find the shortest path from A to F. And we'll be doing that in about 10 seconds for a different graph.
On Friday when we were talking about Hamilton circuits,
Mm-hmm.
do we ever have like one of those generalized statements of how you can count edges or vertices and figure out if you've got a circuit?
No.
No, that's kind of like just, you gotta look at it, right?
Yeah, I don't think there is an easy version of that.
Yeah.
We're still downloading.
Wow.
We can just cancel those downloads.
So in our SLP, we make solid jabs about network quality here. Do we get extra credit?
Definitely get like credit from your friends.
Brownie point.
Yeah. Yeah, I kind of had this fantasy that like the week before Thanksgiving nobody would be here, so I'd get a close parking spot and the network would be fast. But instead I think everybody's panicked, so they're all like here doing extra stuff.
I mean, there's fewer people here, I think.
It feels like it.
Class for sure.
Yeah, it seems like we're missing a couple people in class, but so, ooh,
Well, we rarely have
That is not you.
Hurry, Bowen.
full house.
bring it, yeah.
Bowen is not right there.
Oh, right.
That dude Daniel is only here, he's only not here till after this lesson. So. I don't know. I think I threw away though. I guess there's just not that many people in this class.
Looks like we should have an Euler path in that one.
Yeah.
Is that right? Exactly two odd
Beauty.
nodes.
Yeah. Seems to be right.
Sorry,
Bang,
nodes are
bang,
degree.
bang, 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 bang.
Is it two odd degree nodes or two 3-degree nodes?
2 odd degree nodes.
Yeah. So be
Because if you got a degree 7, you can go in and out 3 times, and then you got an extra one that you either
Do they
start
have
or
to have the
end.
same degree?
I don't think so.
the question is if you can get there and get out, right? It's
Yeah.
not necessarily, you just don't want to get stuck.
Yeah, if you have an odd degree, you can get there and get out n times, but there's going to be one extra time when you only have one edge. So you can use one of those to start and one of those to end. If they're all even, then you can find a path, a cycle. Did anybody figure out our questions about Euler versus Hamilton? Jordan and I figured it out. I took a picture.
What, a graph that is it?
Yeah.
Well, I did find an example.
So Hamilton and not Euler, and Euler and not Hamilton. You found one?
I found one, and I think it was, I'm trying to remember if it was an Euler without Hamilton or Hamilton without Euler.
Do you remember it, or?
I do remember it,
Well, then we can discern which one.
and it's pretty much the exact same as the one last time. I don't think it's connected.
Okay. So you're not gonna have a Hamilton, right?
I don't know, seeing, sorry, we're not gonna have
think Hamilton should be Euler without an alpha, without the earlier. I think.
That's,
Is that it?
Let's see. I think it has a Hamilton.
yeah. No,
I
it's
think
not.
that one hurts us.
It's not, because that one node with 4 routes has to go through at least 3 times, I think.
Hamilton, you can only go through each vertex once, right?
Yeah, and I think we gotta go through this one twice.
Yeah.
But it is.
So, okay, so that was the,
Yeah, so we want Hamilton,
I knew that was one of them.
not Euler.
Well, doesn't that one go through, oh, no,
You could do an Euler on that, couldn't you?
You could go. Now you broke it.
Yeah.
So that's got a Hamilton, bang, 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 bang.
Yeah.
But we've got 3 and 3 and 3, so there's not gonna be an Euler path.
Backwards.
So kite.
Okay. So yeah, some Hamiltons don't have Euler paths, some graphs with Euler paths don't have Hamilton paths.
So there's no real blanket statement where you can say.
There's not a real strong blanket statement we could make.
It just depends on the graph.
Yeah, which is good because it keeps things interesting. And like I say, we start to border on these so-called NP hard problems, which we'll be talking about next week when you try to address this question in general.
Now, my hunch for this Dijkstra's algorithm is that it's A, gonna be recursive, and
Sure.
B, it's probably gonna be similar to the knapsack problem.
No.
Okay, then C, we can solve that problem in that way,
Yes, we can probably solve it that way.
but that's probably not the most efficient road.
It's probably got a natural recursive solution, but it works well with iteration as it is. All right, so here's the idea. And again, I think I'm missing some umlauts somewhere. But I think I got the J and the I in the right order. So find a path, find cheapest. Path from A to Z. And I'm gonna do this with this particular example rather than present it in general and then try to apply it. We'll work on the example itself. So here's our procedure. Start with node or vertex A. Mark visited. So I'm going to circle a node in green to indicate that we've reached that node. It's been visited. Okay, find node closest to our set of visited nodes. Oh, we gotta do something else in here. Mark tentative distance. Mark a tentative distance to all other nodes as infinity. So right now, we don't know if we can reach any of these nodes with a path less than infinity length. We don't even know that they're reachable. Node A, though, we know we can reach with a distance of 0. Okay, so I mark a tentative distance to each of our nodes. Find the node that's closest to our set of visited nodes. Well, our only visited node right now is A, so we want to find the node with the shortest edge distance from A. And we have exactly two edges. We have an edge here to C with a distance of 2. We have an edge here to B with a distance of 4. 2 is the shortest distance, so that's the edge that we're going to add to our graph, our path. Okay, so find the node closest to our set of visited nodes. Add that to our path. And then we do what's called relax the distance to that node. So here's the idea. If we know that we can get to this node in a distance of 0, and the shortest edge from here to C has a distance of 2, we know we can get to C with a distance of 0 plus 2. It's possible that we already found a shorter path. So I don't want to just set this equal to this distance plus 2, but I want to take that distance, which is a 2, and compare it to the tentative distance. If the distance we just found is smaller than the tentative distance, I'm going to update that distance. If it's bigger, I'm not going to change the distance. Okay, so in this case, we can get here with a distance of 2. 2 is smaller than infinity, so I'm going to change this distance to 2. And I'm going to record how I got here. Well, I got here from node A. And now I'm going to mark that node as visited. I get to use go-tos in this class. And I'm going to go back to that part and do this again. So find the node closest to our set of visited nodes. Well, which nodes are directly connected to our set of visited nodes? There's B, there's D, and there's E. Everybody see that?
And B is the closest one.
Yeah.
And B is the closest one. It's got a distance of 1 right here. That's a distance of 4. D is 8. E is 10. So this is the closest node, and this is the edge that takes us, yes?
So to complicate things even more, what if 2 paths have the same cost?
Doesn't matter. You can pick either one. Yeah.
You wouldn't want to look onward?
No, you only look at the ones that are directly connected to your set of visited nodes.
But say you're in a situation where we're looking at C right now, right?
Mhm.
And say you're in a situation where you have an option that has 2 and another option that is 2, and one of the options with 2 leads to an option with 8
Mhm.
with no choices, and the other option with 2 leads to an option of 5.
Right.
So,
It'll work out.
It'll work out because of that little tricky statement about the closest to our set of visited nodes.
Yeah.
It kind of checks everything we've been to and it finds the closest thing from there. So
Right.
once we make it to there with our first set of 2, we'll have another closest node with another set of 2, and we'll try the second set of 2, I think.
Yeah.
I'm gonna keep watching that.
Yeah, it's a good question, and it takes some head scratching
Yeah.
to convince. All right, so we're back here. Find the node closest. That's going to be B. We're going to add that to our edge, and then we're going to relax the distance. So right now the distance is infinity. We can get there. The distance to here was 2 plus an extra 1. This is a distance of 3.
Don't we also check 4, so we go like 4 would be, that's the distance of 4, A to B, but then we see that we also have the route A, C, B, which is 3.
Okay, back up. So we're right here. We're trying to find the node closest to our set of visited nodes.
And we're going from C to B and A to B, and we see that C to B is smaller, so we use that one first.
So we use this one. Yeah, so here's a 4, here's a 1, here's an 8, here's a 10.
Right, and the
Right, 1 is the closest to our set of visited nodes. So we're going to use this edge. Took 2 hops to get to C, plus 1 is 3. 3 is smaller than infinity, so we know we can get here in a distance of 3, and our path is however we got to here, which was A, followed by this node. So A and C gets us to node B with a distance of 3. And then we mark that node visited.
Maybe store the whole path, not just where we came from.
Yes. Because if we don't, yeah, I don't know if you have to. I think I've tried it, just storing where we came from, and we get into ambiguities. But I got ink, got a new marker. I'll store the whole path. Maybe not necessary. All right, node closest to our visited nodes that we haven't already visited. Looks like it's just going to be D and E. And D has a distance of 5. So we're going to pick on D. Distance to D, along here, 3 plus 5 is 8. 8 is better than infinity. So this is a distance of 8, and we used A, C, and B. And now that's a visited node.
E.
And then E is a distance of 2, Z is a distance of 6, so we're going to go with E. And that's going to be 8 plus 2, this will be 10. And it's A, C, B, D. And that's visited. And then here's a 6, here's a 3. This is going to be the closest node. 10 plus 3 is 13. And it's A, C, B, D, E. And that's the node that we were trying to find, so we're done at this point. And our shortest path is A, C, B, D, E. So, bang, 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 bang. And I'm wondering if this is really necessary or if we just need the node. I think there may be cases where we come back and we take another link off of the vertex. But maybe not.
If you end up back at the same node, doesn't that mean you've gone through a loop or something?
Well, this is always tricky to start modulating these things on the fly. But let's
I
see.
guess let's do it that way, we should just do that.
Oh, no. This is the nature of discovery. So let's back up here and let's change this.
Alright, now we made it interesting.
Right, so at this point we were at D, the closest node is here, so we can get here in a distance of 10.
Pretty much all my questions.
And we'll visit this. And now the closest node to the nodes we visited is Z going through here. So we got 8 plus 3 gives us 11. And we visited this.
So what's your path? A, C, B, D, C?
But if we back up to D, and we know that D came from B, yeah, that works. So maybe we just need the last node we visited.
So then, because then your path is A, C, B, D, C, right?
Yes,
And you never actually go to E.
we never actually go to E.
Okay. So that kind of solves the problem that I was thinking of in my head then.
Okay.
So here's another conceptual problem. What if you had a grid of 4 nodes in a square formation? Each one has a length of, they can travel laterally, up and down, left and right, with a distance of 1 on each one.
Like
Or,
this?
sorry, I was thinking 16 nodes to make it actually interesting.
Okay, so 4
But
by
I guess
4.
9 would work just fine too, to keep things simple. But yeah, but they can each travel laterally, yeah. And they each have a distance of 1 between them and their node next to each other. So how would this handle it? It would just iterate through every single node,
Do
basically?
you want to go from a corner to a corner?
Yeah.
Yeah, so
First step.
we'll visit this one. It will pick one, right? Our closest node is either this or this. So it'll pick one, this will have a distance of 1, it'll pick another,
And so it's
This will have a
basically just
distance of
random
2.
at that point.
yeah,
But then at that point, no, okay, because it doesn't matter about the total distance. Okay.
right, so it's finding a shortest path, may not be the shortest path,
So you don't get stuck down any paths.
right,
This is the point.
Okay.
Because what I was thinking of was kind of like, you have one path and you have a fork. You have two different size paths. Like, kind of like a Y. Like,
yeah.
you know.
So like here, we went down this path which was shorter than this one, but didn't actually take us to a node that we were gonna include in our final
right.
shortest
Once you get
path.
to E, you realize that it's way too long, so you
Right.
rush back to D. Because
Yeah.
it's all the nodes that are close, right? Okay.
Yeah,
So I'm just trying to think of counterexamples to this, and I can think of one, but I'm not quite sure if I'm correct in my thinking. I need
Okay.
to show it off.
wanna do it on the board?
Yeah, of course. So wouldn't Dijkstra's algorithm take you through here instead of going back to there?
All right, cool, let's try it. So, tentative distances,
Yeah.
that's okay. We won't worry about recreating the path. All right, so here's distance of 0, shortest. So this is visited. So shortest edge is right here. That's going to be a distance of 1. And it's visited. Closest collection is going to be 1. This becomes a distance of 2.
So now, at this point, it's a gamble. It might go another step further on that path, but it might also go down the other one because they're the same distance, A to B.
But either way, once it gets larger, then it's going to take one of the two on the left side.
Yeah, it
Once you
should.
hit 3, you should take 1, 2. Then you're gonna take another 1 and hit 4. You're gonna take another 1 and hit 5, and then you'll take another 2 instead.
Because
So there's extra work in this one, but I
Yeah.
think you'll still get the right path.
Because in this case, it's sort of like taking resistors and electricity, and then to simplify the circuit, you would do the resistor simplification tricks of adding them together or
Right.
adding their reciprocals together. So it's kind of the same thing. Once we've visited some nodes, we know that the point from one end to the furthest point can be simplified down to basically one node that has a length of 3 in this case.
Right.
Because now that you're at 3, you would take the 2 on the left, right?
Yeah, I don't think I wrote the algorithm like that, but I think that's what you want to do.
You must look at the distance as the distance to itself plus the way of the edge.
Right.
Exactly, yes.
Because like you were saying, you have to be, less than infinity, right? Well, in this case, you would be looking at 3 and have an option to go to 2 and just have a path of 2.
Right.
Yeah. I don't necessarily know how to represent that in words, but that's the desired behavior, right?
Yeah.
So, I got a quick question on this.
So I think I should say find the node closest to our source node from the set and adjacent to the set of visited nodes. And add that to our path.
That works.
So find node closest to,
Which means that in the example that I suggested, it would iterate through every single.
right,
I was wondering about that.
closest to source node.
But either way, you're gonna want to put 5 on that one. 4.
On my suggestion.
Yeah.
One,
Looks like
two,
you're ready.
three, 4.
Yeah, 4.
Adjacent to our visited nodes.
You are, but it could iterate through every
Oh,
single
yeah.
one in an S curve,
it's probably gonna have to iterate through everything, but eventually it's gonna wind up at 4 no matter what.
Exactly.
But I think your path can be totally random, what it decides. Because it could be straight through, or it could be the side.
There
like the
is,
side,
there's a map thing that shows.
Alright, so before this one kicks in,
Right angle grid, the distance from point A to point B is the same as when you.
this will be a distance 3 from our source node, this is a distance 2, so I think at this point we visit that one. And we said it's distance to 2. And when you relax, you need to relax all the nodes adjacent to the node that you just marked. Right, so now we know that we can get to this node with a distance of 2, so we could have relaxed this to a distance of 3. Now we know we can get to this node in a distance 2, so we could relax this to a distance of 4.
And then you check the other ones to see if they're better.
Yeah, so now the closest node is going to be this one, which is 3. So we'll visit that, but we'll relax this one to 4.
And then you would probably still have to go to the 4 on the right side.
You might pick this one or you might pick that one because they're both equally good. If this node was not here, we might pick that path or we might pick that path and it wouldn't matter because they were both a distance of 4. But if we pick that one, we'll visit it. We'll relax this to a 5. And now it's going to say this is a distance 4, so we'll pick this, visit it, leave that as a 4.
So basically we are doing the search tree, right?
It's a form of a search, yes.
We are going all the way to the end from all the sides, so.
Yeah.
Doesn't,
But we don't necessarily travel every path.
yeah, in some cases we are just putting them out.
Right, if we had a
Yeah, that
100,
yeah.
200, right, we'd never travel that
Yeah.
set of edges.
It's not so much that it's like a search tree as it is that you're reevaluating everything after every move.
Yeah.
You're looking at all your options each time you make a move and deciding if you've made an error and gone down a path that you couldn't foresee at the time was going to be longer, but you do see it now.
Right.
So yeah, it's constantly reevaluating everything.
Alright, so let's try a more interesting graph than my first one.
Kind of like a more efficient knapsack problem, like I suggested earlier.
Yeah. I'm ripping off this example from Wikipedia because I remember it was a fun one to work through. And it was very non-obvious.
Was Dykstra a mathematician or was he one of these philosopher guys?
He was a mathematician. He's the one who, when he went to get married, he said computer scientist on his license. And
Right,
I told him
right.
that wasn't an occupation.
Gotcha.
7, 9, 10, 15, 11. And 6 and 9 and 14.
Where are we trying
Let's
to go?
to B.
About that one edge,
There's one without a weight.
What?
Next
Oh,
to
yes,
9.
there it is, yes, yes. Oh, well, that changes things.
Yeah. Like I say, this is a fun one to work through. All right, so let's go from A to Z. So initial distance is infinity. A has a distance of 0. That's where we begin. So we visited that.
Now we go down to the right.
So now we're going to go down to the right. We're going to visit this node. It has a distance of 7. And now we're going to relax all the nodes adjacent to that node. So 7 plus 15 is 22. That's smaller than infinity. 7 plus 10 is 17. That's also smaller. So we know that we can get to this node in 17. We may be able to get there by a shorter distance like this.
Yeah.
But for now, 17 is the best that we found by using these two nodes.
Next.
All right, so now find the node closest,
That's 9.
and that looks like a 9. And 9 is better than 17, so we'll relax that distance. Or we'll replace that distance. All right, relax all the nodes adjacent to that vertex. So 9 plus 2, this has a tentative distance of 11.
Next one's gonna be 18, or sorry, 20.
9 plus 11 is 20, that's better. And that we've already visited, those are the only ones adjacent. All right, find the node closest to our collection.
You take the 2 up to the 11, correct?
Could
So,
could either go up 2 or up towards the 11. They're the same.
Yeah.
Or sorry, no, it's gonna be towards the 11.
it's gonna be the 2 up to the 11.
Yeah.
That's gonna be our closest.
To the 11.
9 and 2, 11, so that is the distance, we mark that as visited. We relax the nodes. So 11 and 9 give us a 20. And that's the only thing adjacent. Now find the node closest to our collection.
It's gonna be the 9, wouldn't it? The route from the 9 to the Z.
And it looks like the 9 to the Z, yeah.
That definitely would be what it is.
So there's 20. And I think we're done. That was not as interesting as I thought.
Yeah, I was gonna say,
So at this level, you still can't kind of see the path, but I think as these get larger and larger,
Yeah.
it's harder and harder.
Yeah, and as you have more edges on each vertex, you start going down other paths that don't end up being where you end up with your final path.
Yeah.
All right, so that's Dijkstra's algorithm. You got one homework question that asks you to apply it to a graph.
Is there any instruction for like if you had, I don't know, like weights on the points? Like if you were supposed to use this to find the quickest time between points, and then at each point you have to do a task that.
Like one point would be
Interesting.
more valuable than another. So there's
No, just like a time penalty of going through a particular vertex.
Yeah.
Could you turn it into a problem like this by just adding that weight to each of the adjacent edges, maybe?
that's what I was gonna say. If you sort of normalize it all the way through and add
Yeah.
it to the adjacent edges, like you just said, or incident edges.
Incident
Probably what
edges.
you would do, yeah.
That might work, but I don't know. I gotta think about that.
It would be tricky doing it properly.
Yeah.
So for instance, if the 11 up in the upper left carried a time penalty of +3, then
Mhm.
yeah, I think it would work out the same if you just added 3 to the 14 edge, the 2 edge, and the 9 edge.
But then if you're going in
No,
and
'cause
coming
you
out, you hit 3
Yeah.
The
times.
9, you
Yeah.
add it as you go to that.
So you might need to change it to a directed graph.
There you go.
Oh yeah.
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 Or a directed path. The graph doesn't strictly have to be directed, but the
Right, the
path
paths you're
does.
looking for.
So as you go to a point, you consider it added to that.
Yeah.
You can just add half to each edge.
So that's like a layover almost.
Yeah.
If these were
Yeah.
paths to different airports, that's like having a layover in one, whereas you can do a direct path to the other.
Mm-hmm.
Or the
Yeah.
Right.
of light in there or something.
Yeah, it's an interesting modification. And I don't know if Dijkstra itself would work.
That's cool.
I mean, yeah, it's just a little modification.
And like I said, subtle changes, like if you allow these weights to go negative, things change.
Oh jeez.
Yeah.
What does happen?
I don't think Dijkstra's algorithm works if you have negative weights.
Why not?
Yeah.
Yeah,
Can
that's
we
what
give
I
it a go? Do we have the time?
I don't know if I can come up with an example where it won't work.
in this 2-day week. Can we
Oh.
do this negative?
Um,
It seems like it would work. Because if you say that the negative would be, it's lower still, it's strictly lower, less than, so it would be closer, right? Than a 10 or something. You have a -3.
As long as you don't do anything silly like trying to normalize those negatives out, like I suggested a while ago,
Yeah.
you should be fine.
It's one of those things where it's like, a gut feeling is that it should work.
it's not the fastest algorithm if you have negative weights, but I don't know if it works for negative weights or not. That's from Wikipedia.
How fast is this
It's actually
algorithm?
functionally works with edges.
It
Is
seems
it-
to be kind of slow because you're checking everything.
Why would it?
Is this algorithm the bubble sort of pathfinding algorithms?
This is pretty efficient,
Okay.
I believe. But it says the Bellman-Ford algorithm can be used on graphs with negative weights, unlike Dijkstra's
I saw a
algorithm.
mention of that.
The Bellman Ford.
Toss some negatives in there, let's see if it breaks.
It won't break, but I don't think it will give us. And I think what's going to happen is like we said a little on Friday, if you offset everything to make your paths non-negative, that might help you, but
Well, why don't you try it with
I just wanna see it break.
let's see it break.
Change your mode to negatives, toss some dashes in front or something.
All right, I'm game. I was gonna wrap up with Prim's algorithm, but Prim's algorithm only takes about 2 minutes to go over. So let's make some infinities. I hope they never find out this ink is like toxically absorbed through the skin. That'll be that. I mean,
kindergartners?
And then suddenly
Yeah,
all
it's
of
been
mathematics' greatest minds just keel over dead one day because of
We
it.
gave you the eraser for a reason.
yeah, I know.
And then we really wonder why that one.
At least children's not.
Yeah, I like chalk.
Like the markers we talked about.
All right, so
Okay, so we start with this
to
one.
start with A,
Go down.
I'll throw a negative up here just to like.
Okay, then you start
Okay,
with
that'll
14.
make it too ugly.
Yeah.
So then you start with 14, and that would be clearly the most advanced path.
Yeah, and this has a distance of negative 14.
Is that a negative 2?
Yeah.
Yes, it is.
Next you go down
The next shortest is gonna be,
Well, you gotta relax first.
yes.
Oh yeah, relax all of these. So this is negative 16, and this is negative 14 plus 9 is negative 5.
Oh,
negative
right,
14
right, I'm
minus
going
2.
from the, yeah, okay. And suddenly it's solved.
No, it's not.
Well,
Sure?
Well, no, I mean if I have this, my shortest path is going to be along there for sure.
The negative 16 would be better than the negative 5.
It's
So
already.
you'd
That's
go
true,
to,
that's
you'd go
true.
down to negative 2 to negative 16. I think it works.
So what about here?
Okay, we'll normalize it again.
So
Yeah.
what's my next
Negative 12.
node?
We've got
Well, hang
negative
on.
12 in the
You
middle.
got negative 16, and then the z would be, in this case, negative 13, right? Not negative 5. The z,
Yeah, so z becomes negative.
you have to renormalize because you changed to 1.
This is the Z.
All right, so hold on. Let me change this. Let's do it like this. Here's a distance of 1.
It's changing.
Distance of 1, so it's going to go to E, right? With a
Yep.
distance of 1, I'm going to relax those nodes. This will have a distance of 3. This will have a distance of 2.
Uh-huh.
What's it going to do next?
Obviously, you're having negative 1100.
That's not adjacent, right?
Well,
It's
no,
going to
it's-
choose either this node or this node,
It starts going from E to Z.
right?
which is
So this
negative.
gets relaxed to a distance of 2, it visits
I see the
that,
problem.
and I'm done.
Yep.
But I didn't find my shortest path.
You didn't find that.
Okay, but if you modify the algorithm to keep trying.
If you keep trying, you might, but then you're at a really combinationally
Got it.
explosive.
And then it's not Dijkstra's algorithm. So
Yeah.
now I see the problem.
So what's the other algorithm that they mentioned?
The Bellman Ford? Is that
The
what they said?
Bellman-Ford, that's an ungraded homework question. I don't know the Bellman-Ford algorithm, but,
Let's ask Wikipedia.
well, yeah, that's where I read
It's
it.
gonna be real interesting if it's just, oh, it's Dijkstra's, but you keep trying.
Yeah, just do it in the mirror. Right? All right, so there's Dijkstra. We'll talk about Prim's algorithm on Monday, or tomorrow, and
I say, wow, is that a short week?
yeah, really
Like
short.
shorter.
week. Prim's algorithm tomorrow. We can wrap this up tomorrow, and then I'll probably start talking about formal languages just to introduce some of the terminology. And our last week will be all about formal languages, automata, finite state machines, Turing machines, computability. And we'll end on good stuff.